Good morning, good afternoon, good evening, depending on when you're watching this. Welcome to this next video on exponential equations. So let's get right into it. So my idea is to take you through the simple type of conventional exponential equations where you need to just get them into common bases and equate the exponents. And then we're going to go into the ones that are a little bit intermediate that needs you to actually factorize and take out a common factor there. Then we're going to go to the complex ones where there is a k factor that needs to be applied there. And then lastly, we're going to look at the ones with sets in them. So I hope you guys are excited. Let's jump right into it. Alrighty. So let's take these easy ones right here. Let's say you have a 3x. Let's say you have a 3 to the power of x minus 1 that is being subtracted by 27, which is equal to a 0. So how do you solve this? These are the easy ones where you just need to get the powers to be by themselves on one side. So I'm going to isolate this 3 to the power of x minus 1, and I'm going to put the 27 to the other side. And remember, the side needs to change. It was a negative there. It becomes a positive on the other side. Then I want to get the 27 to be a base of 3. And 27 is a base of 3. It's 3 to the power of 3. Then now that the bases are the same, I could just make the exponents equal to each other. So I'm making x minus 1 is equal to 3. Then I just take the minus 1 to the other side. It adds with the 3. And so x is equal to a positive 4. Alright, so these are the easy ones. Let's have a look at the other easy ones, and particularly ones where the x is not an exponent but rather has an exponent. So what about these ones here, which says 3x to the power of 2 over 3 minus a 12? How would you go about solving these? So it's pretty much the same idea. You want to isolate the guy that has the power, or the power that has the x with it. So I want to take the 12 to the other side. I get a 3x to the power of 2 over 3 equal to a positive 12. At this level, you would want to divide by 3 on both sides. Why? Because I want these 3's to cancel. So when that happens, I have an x to the power of 2 over 3 that is equal to 12. Then at this point, all you need to do is to get rid of this power. I need to times with the reciprocal. So what is the reciprocal of 2 over 3? What multiplies the 2 over 3 so that I end up getting a 1 as my answer? So the answer to that, it has to be multiplied by a 3 over 2. So that's the only way I'd get a 1 there. So what I'm going to actually do is I'm going to put this to the power of 3 over 2. And I'm going to put this to the power of 3 over 2. And why? Because this 2 over 3 times the 3 over 2 would give me x to the power of 1. And here, if you have a 12 to the power of 3 over 2, you could just easily use your calculator there. Yeah, you could just easily use your calculator there, and what you would get, no, sorry, I forgot something. The 12 divided by the 3 here at the top would give me a 4 here in the bracket. So actually we have a 4 that is to the power of 3 over 2. Let me just erase it down here as well. Sorry, my mistake. down here as well, we would have a 4 to the power of 3 over 2, and that, if you plug into your calculator, it's just easily 8. And how am I getting the 8? Because a 4 to the power of 3 over 2 can be written as the square root of 4 to the power of 3. Remember, this denominator here could go out and be a square root. And 4 to the power of 3 is a 64. So I'm looking for the square root of 64, which is just easily an 8. So that's how you would solve that type of question. So these are the easy ones. And I want us to take this whole idea of what we just did there and try and apply it to these intermediate ones where we kind of need to take out a common factor. And you will see that the way we go about solving it is slightly different, actually. And let me just rewrite this whole question. It looks something like that. So what is different about them? We realize that we have a power that has an x there, and we have a power that has an x there. So now it's not just one thing that has the x there, but instead it's two terms that have the x. So what I would like to do is I would like to grab this guy and bring him over to the left hand side. And when I bring him over to the left hand side, remember we still have the 3 to the power of x plus 2. And this is a whole term. It's one big term. So I bring this whole thing over and it becomes a positive. And that's how it looks like, equal to a positive 42. Then at this point, I like to split up those guys. And what do I mean by split up? Remember, if I have a 3 to the power of x and I'm multiplying this with the 3 to the power of 2, right? I'm going to add those exponents and I'm going to eventually get a 3 to the power of x plus 2. So I have something like this. I would like to go back to something that looks like that, where I split it up. So I'm going to split up this guy here, which is going to be a 3 to the x times a 3 to the power of 2. The rest of the equation. And why am I splitting him up like that? Well, I'm splitting him up like that because I want to notice that here there's a common factor that I can take out. This 3 to the power of x and this 3 to the power of x is a common factor. So I want to take it out outside of my bracket. Open my bracket. I still have my 42 on the other side. So 3 to the power of x times what would give me back to this full first term? It has to multiply with the 3 to the power of 2. 3 to the power of x times what would give me back to this full second term there? It has to be multiplied with a positive 5. So this 3 to the power of 2 plus 5 would just give me 14. So I end up with a 14 equal to a 42 there. And if I divide both sides by 14, then I end up having something that looks like this. 3 to the power of x, 42 divided by 14 is just a 3. And at this point, the bases are the same. I could just make the exponents equal to each other. And so x is equal to positive 1. I hope this makes sense. So these are the ones where you need to kind of factorize a little bit. Let's look at other ones that are slightly different from these ones and how would we go about solving those. So what if you have a 125 with the 3 to the power of p? This is being multiplied with the 125, and on the other side you have 27 with 5 to the power of p. So at this point I'm looking at this and I'm like, we have a power of p there and we have another power of p there, but the bases are different. So what would I want to do? I would want to collect all the powers of p on one side and collect all the constants on one side. So what I'm going to do in the first step is I'm going to divide by 27 on both sides. Why? Because the 27 and this 27 are going to cancel each other. And then on the right hand side, I'll end up having 125 over 27. I'll just put this in one big bracket, and I still have this bracket of 3 to the power of p, and all of this is equal to 5 to the power of p. So that's what I did in the first step. In the second step, I want to now divide both sides by 3 to the p. Why? Because the 3 to the p's on the right hand side are going to cancel. And those 3 to the p's on the right hand side, once they cancel, on the left hand side, I mean 125, you'd have 125 over 27. And on the left hand side, you'd have a 5 to the power of p divided by 3 to the power of p. So what law am I going to use now? I'm going to use the law that says if I have a over b and this is all to the power of p, the a receives the exponent of p and the b receives the exponent of p. So it ends up being a to the power of p divided by b to the power of p. So what I have is the guy on the left hand side, on the right hand side, and I want to rewrite him as the guy on the left hand side. And that's what I'm going to do to this power of p that I see on the right hand side. So let's work with that. I'm going to just take out the p there. Sorry, the denominator is 3. And it looks like that. Then for this guy, I'm going to write them as prime products. So the top is a 5 to the power of 3. The bottom is a 3 to the power of 3. And this follows the same logic of what I just did for the top. I just take out the 3 and I rewrite it like this. Then I notice that, ooh, the fractions inside are the same. So the bases of these exponents are the same. So the exponents can be equated, can be made equal to each other. So I'm going to equate my exponents, and so easily p is equal to a 3, or 3 is equal to a p. Either one makes sense. All right, so there we go. That's how you'd go about solving those. So now let's move on to the complex ones. And these complex ones are ones where you need to apply k-factor. So what if you have 2x to the power of half, right? That is being subtracted by 3x to the power of fourth, that is being added with the 1. How would you go about solving this? So one thing you need to notice is that we need to use k-factor. And the way I'm going to use k-factor is that I'm going to call this guy k. Not the second guy, but the lower exponent, the one with the lowest exponent there. I'm going to call that k. So I'm going to say x to the power of y over 4 is equal to k. And if I square both of these, this equation here, if I square both sides, a quarter squared would just give me a half. And a k, if I squared, I get this guy. So this guy looks like the first term there, right? So I'm going to substitute k squared for that guy. I have my minus k there, and my positive 1 is equal to 0. So this is clearly a trinomial that I need to factorize. If you don't know how to factorize that trinomial, the way I go about factorizing these, once I start seeing a coefficient there, I just take that coefficient and multiply it with the constant term there, and end up getting k squared. It goes away there. And here in the last term, 1 times a 2 is just simply a 2. I factorize these. Factors of 2 that add up to give me a 3 is a minus 2 and a minus 1. But just as much as I multiplied with the 2, I need to come and divide my factors inside there with the same 2. So I end up getting that. The first one simplifies, the second one does not. So I leave it like that. And at this point, you could just easily solve that quadratic equation. Take this first bracket, make it equal to 0. Or the second bracket, make that equal to 0. And then at this point, I want to substitute back my what k is equal to. Remember, we took k as x to the power of 1 over 4. So x to the power of 1 over 4 is equal to a 1. You put it to the power of a 4, you put it to a power of a 4. X is just easily a 1 for one of my solutions. For the other one, x to the power of a 4th is equal to a positive a half when it goes to the other side. You put this to the power of a 4, you put this to the power of a 4, x is equal to a 1 over 16. 1.5 to the power of a 4 is 1 over 16. So we have these two solutions of x, and both of them satisfy the equation at the top. So we've done these complex ones. Let's do one more. What about something like this? X to the power of negative a half that is being subtracted by x to the power of negative a half, all equal to 20. So we have this again. The middle one is always almost gonna be your k. So let's bring everything to one side. So if I do that, I have x to this minus x to the power of negative a half minus 20, and I'm saying k is the middle one, which is the x to the power of negative a half, like that. And almost always, if you square it on both sides, square the half, you end up getting a negative a 1. So what does this mean? My k squared is there, my minus k is there, and this is minus 20. So I'm looking at factors of 20 that add to give me a minus 1. And those factors are a minus 5 and a positive 4. Right? Then now that I've solved my quadratic, I can just easily take each bracket, take the k minus 5, make it equal to 0, k plus 4, make that equal to 0, and so k is equal to 4. Substitute back what my k is. There's the first one. So what do? This, I take the reciprocal of that, which is negative 2 over 1, and I'm doing the same, the negative 2 over 1, and so x is equal to, if you plug in 4 to the power of negative 2 over 1, you should be getting 1 over 4 squared, which is 1 over 16. Right? Same with this side. I have x to the power of negative a half is equal to a 5. I do the same, negative 2 over 1 as an exponent, negative 2 over 1 as an exponent, so x will end up being, that would be 1 over 25. So there's your two x values. X is equal to 1 over 6, and x is equal to 1 over 25. All right, so we've looked at these, and These are the complex ones that need trinomial factorization. Let's look at the ones where there's surds involved. So you would have seen with all the ones that we've solved, we've never actually needed to check. The ones with the surds, we always need to check our answer. And what do I mean by that? I'll show you what do I mean by that later on. So if you're given this, how do you go about solving these? The best way to do these is to separate the root, the guy that has the root, with the rest of the terms. So the rest of the terms in this expression is just the x. So I'll take the x to the other side, and I'll end up having the root of x minus x 3x minus 2 all equal to an x. And once I've done this, the whole objective of doing this is so I get to this point where I can square on both sides. Why am I squaring on both sides? Because that's the only way to get rid of the root. So I square there and I square there, and so I end up getting 3x minus 2 is equal to an x squared. Then at this point, I just bring everything on one side. I'll get x squared minus 3x plus a 2 on one side. And once I have it like that, I just look for factors of x that add to give me a negative 3 to minus 2, or factors of 2 rather, that add to give me a minus 3 to minus 2 and a minus 1. And so x minus 2 is equal to 0, x minus 1 is equal to 0, and so x is equal to a 1 and x is equal to a 2. So we got these two solutions. But what we need to do every single time when we're solving these is to always check. So take the expression as it looked initially, right? And if we do that, alright, so let's check for the first solution there where we got x is equal to 2. So we just substitute 2 wherever we see x in our original equation, and we want to see, is this gonna make sense? 3 times 2 gives me a 6, minus the 2 is a 4, so we have square root of 4 minus a 2. Square root of 4 is a 2, and so 2 minus a 2 does give me a 0. So that one does make sense, right? So this solution that we have down here definitely does make sense. Let's try the next one. So our next solution we want to try is the one where we found 1 as the solution. So if you substitute 1, we notice that 3 times 1 is a 3, minus a 2 is a square root of 1 that is being subtracted by 1, and a square root of 1 is just the 1, and a 1 minus a 1 is a 0. So this does make sense too. So both of these solutions satisfy that equation at the top, but not every single time do they satisfy. So in this one example they definitely do, but in some of them they don't. So you always need to check. So let's try another one of these type of surd equations, and I think this will be the last one for the evening. So let's take the square root of 31 minus 10d, and this is all equal to 4 minus a d. So how do you solve these? So these are already separated for us. All that we need to start by doing is to square on both sides. So you square the root on this side and you square the expression that you see on the left hand side. And if you square a root, you just get the stuff underneath the root. Right? If you square that binomial, remember if you square binomial, you need to write it twice and then expand it. There is no easy way of doing it. You don't just square the first one and square the second one. That will not be correct. You have to do it this long way and apply your FOIL. 4 times a 4 is a 16. 4 times the negative d is a negative 4d. Negative d times a 4 is a negative 4d again. And then lastly, a negative d times a negative d is a positive d squared. So we have our positive d squared. Now let me just collect my like terms. If I do my like terms, I end up getting a d squared minus 4. Minus 4 is a minus 8. And then I'm going to add it with the 10. I'll get a positive 2d actually. Not a minus, a positive 2d. And then lastly, a 16 minus a 31 would give me a minus 15. So I get this trinomial. I need to factorize this trinomial. It's almost always easy, guys, to factorize these. Sometimes you might need to use your quadratic formula, but 9 times out of 10 it will be very easy to factorize these. So if I do factors of negative 15 that add to give me a 2 is a positive 5 and a negative 3. And so d is equal to a negative 5 and d is equal to a positive 3. So there's my two values. D is equal to a negative 5 and a positive 3. But let me check these. Let me just quickly check these here on the side. If I check the first one, it was the square root of 31 minus a 10d is equal to a 4 minus a d. I think that's how our expression looked like. So if I substitute 3, I end up getting square root of 31 minus 10 open bracket 3, and I'm trying to see, is the left hand side going to give me the right hand side? 10 times 3 is a 30. 31 minus a 30 is a root of 1, and the root of 1 is just the 1, and a 4 minus a 3 is a 1. So that one works. This one definitely works. So let's try this next one. Let's test the next one. And to test the next one is pretty much the same idea. We need to just substitute into that equation that we have at the top, which is 31 minus 10 in bracket the negative 5, and I want this to be equal to a 4 minus a minus 5. So a 10 times negative 5 would give me a 50 there, but it's going to be a positive, so this ends up being 81. That ends up being 81. So if that's 81, then we have a square root of 81 is equal to 4 plus that, which gives me a 9 as well. And yes, a 9 is equal to a 9. So in this case, this one does work too. But again, every single time with these, you kind of do need to do your checking. So this is me just checking. And like I said, sometimes one of those solutions does not satisfy the equation, and so you need to reject one of them. And the only way to reject it is just to come here and say not equal to. So that will be, yeah, pretty much it. But in this case, they're both equal to, so I will leave it as a d is equal to a -5 and d is equal to a +3. All right, that's it from my side. I hope that made sense. I hope you guys followed. I hope this will help you with your projects. On that note, it's Mr. Malaji signing out. Bye.